So this is not the title of my presentation, but it's Dynamics on Complex Networks. But before I get into the nitty-gritty of whatever we are going to do in the next few hours, uh, maybe I should say where I come from, in the sense that anytime you talk of networks, or like even if you just type the term networks in a search box, often you get things about computer networks, IP networks, and so on. So the idea is that you go beyond that, you take the abstraction of that. It's essentially a network like that, an IP network like this, or any of these wires that are crisscrossing here, they connect some two entities and possibly exchange some information. Okay. So if you take that core idea and look at all other places where this can be applied, then you will see that pretty much everywhere you can think of most of the things as networks. People could, the collection of people could be thought of as networks, because you could draw a connection between friends and even enemies. And you could, of course, for very obvious reasons, think of railway stations, airports as networks, and connections would be the transport that takes place between them. And quite surprisingly, in recent years, even things like climate are being studied from networks perspective. So there are global, what are called teleconnections between various processes in the atmosphere over the ocean. Again, you can always hopefully construct networks by identifying various sort of nodes and some sort of linkages between them. So effectively, we are going to throw out pretty much a whole lot of details associated with specific networks. So you don't worry about what kind of TCP/IP protocol, or what kind of protocol an airline company might be following to, let's say, to schedule their operations and so on. But you just work at a higher level of abstraction, taking into account only the core aspects of such a collection of objects and edges. And then you ask the question, like, what are the various things that can happen in such a situation? Let's say one thing is to study the structural aspects of the network. Maybe there were some talks here about the structural aspects. You don't need to put any dynamics on it. Just the fact that you have a network of things possibly randomly connected, you ask questions about what are the properties of those connections. Is there something that's common to all the networks, independent of all these nitty-gritty details? But another level of study is to put some dynamics on it, get something going on top of the network, and then ask a question: what are the emergent properties? What are the properties that you can actually see on networks that you don't see otherwise, even if there is a flow, for example? So essentially, when we say something like dynamical processes on complex networks, so we are going to use some abstractions of certain processes. So in this case, at least most of my talk would be about diffusion kind of processes. So we'll start from random walk and so on. So that is a detail that we'll get into soon. And also, unlike graph theory, maybe I should say that physicists would often call it networks, mathematicians call it graphs, nodes become vertices, and so on. At least for this talk, we are going to do quite a bit of mathematics, but all difficult derivations or difficult proofs, I'm not going to do it. I hope that you can go back and look up the proofs of those things. Otherwise, we wouldn't be able to go far. But I'll try and give you physical intuition for whatever we are trying to do. That again is to some extent a physicist's way of looking at things. So in fact, I don't know if you've been introduced to the idea of scale-free networks. For long, since the time of at least for 200 years or more, people have been studying random networks. Erdos is one of those persons who had studied it in great detail the last century. But then it turned out that many of real life networks aren't quite random in that sense. And that is where a whole lot of contributions from physicists came about. So you actually look at what's happening in reality rather than construct mathematical models which are in some sense exactly solvable. So there are many examples of dynamics on networks. You can think of traffic flow, just traffic flow outside this university, or spread of epidemics, and of course the IP, TCP/IP protocol, which allows information to be traversed on the internet, migration of animals, even the search problems on internet. We are going to look at it in some detail later on, page rank algorithm and so on. Spread of information or spread of misinformation, power distribution network, a whole lot of things where you can put some kind of network. So this, the thing that you see on the right side is one simple kind of network. Okay, and so when you put dynamics, many things can happen, and so I just took some very extreme kind of phenomena. One of them is this blackout. If you are in North India around the year 2012, there were 2 days when entire North and Eastern India actually did lose power. So you can see that red region shown in the map. So typically, and whenever such major events happen, there is a committee and a report that comes out. And what happens is, it's not something very specific to India. This kind of blackouts happen even in advanced countries everywhere. But ultimately, you can trace it to the fact that possibly some transformer or some node in the power distribution network malfunctioned, for whatever reason. And so that did not work. So the load that it was handling gets transferred to the ones that are connected to it. And they aren't able to handle that load, so they also fail very quickly. And then that gets transferred to the others downstream, and so on. So very soon you see huge areas that are affected, and so that's how a blackout, for example, finally happens. So this is again the same thing, where about 600 million people were affected due to grid failure. And this is again another similar example that I picked up from Pune's newspaper 10 years back. So a road was dug for some pipeline work in one place, but it led to cascading traffic snarls all across the city. So again, it brings to the fact that you are in a connected system. So doing something in one place affects elsewhere. So these are the kind of questions that you'll have to address if you are going to look at dynamical processes. So there are lots of similar examples. You can construct financial network graphs. Sitabra told me to talk of synchronization. Maybe I'll keep it for tomorrow. Okay. So a good part of what I'm going to speak today will be about random walks. It's one of the simplest processes you can think of. Even simpler process would be simply to go from A to B, 2 points on the network. But it's slightly little more involved than that would be a random walk. And this is not just a figment of a mathematician's imagination, but you could do a whole lot of modeling simply using only random walks. So I've listed some of them here, like modeling stock prices. And contrary to what you might think, modeling stock prices is a very old enterprise, both in physics as well as among financial, those who work in the area of finance, okay, more than 100 years old. And in fact, earliest models did use random walk without calling it so. And of course, in computer sciences, quite a bit of random walk is being used in queuing theory. Maybe some of you must have studied that in information discovery, web search, recommender systems, ranking, of course. And there is a lot of random walk used as a model in biology. Some of the things are listed here. And of course, physics, especially statistical physics, a lot of random walk is very, very useful in polymers, traffic models, extreme events, whatnot. So this is just a small list, not a exhaustive list of things that can be modeled. Okay, so this is where I'll begin. So this idea of random walk is not really new. In fact, the first question. Okay, maybe I should start from this. So the simplest random walk is like this. You can see that there is a linear lattice, and that point that starts in red color is your initial position. So you say that the random walker starts at 0. In principle, you can start from anywhere. The results may be slightly different, but just by convention, you start from position 0, and you have a discrete lattice. So the positions are labeled like 1, 2, 3, and so on, and also on the negative side. So you have two different probabilities, one for going towards the left and another for going towards the right. So going towards the left is P. So since you need to conserve probability, going to the right is 1 minus P. So in fact, this was actually first put out as a question in this journal Nature in 1897, I think. I don't see the year here, but somewhere around that time. So this is actually the question. So in fact, the statement of problem is here in these 4 lines. A man starts from a point 0 and walks L yards in a straight line. Then he turns through any angle, whatever, walks another L yards in a second straight line. He repeats this process n times. I require the probability that after n stretches, he is at a distance r, distance between r and r plus delta r from the starting point. So you randomly keep walking and know what is the probability that you will be at a certain point after a certain number of steps. And so this was the question raised by Pearson, published in journal Nature. And in the very next issue, there was an answer to this question from, you can see, Raleigh. You might recount this name in several other, associate this name with several other phenomena in physics. But Raleigh basically said that this question was already studied some 20, 30 years back, and here is the result, and he gives this distribution. Okay. So essentially, we are going to show some of these results as we go along. So this is, in some sense, the simplest possible setting for a random walk. You can create much more complicated random walks. You can bias the walker and do various kinds of things, but this is possibly a simplest setting. You just have a one-dimensional lattice. There is one walker starting from position 0. Okay. Now the central results are actually shown here. The distance traveled goes as root n, apart from all the factors p, 1 minus p, and so on. N, yeah, so n is the number of steps, and here the number of steps is also equal to the time. So the distance traveled in some sense is proportional to square root of time. That is characteristic of random walk. And in general, it's also characteristic of standard diffusion process. Okay. So let's see how this comes about. Okay. So now I'm going to start doing things. So we'll go back to the same setting. And we'll associate two probabilities. probability going to the right is P and probability of going to the left is Q. Okay. And to fix everything, you can assume that the distance between two lattice points is L. It doesn't matter, it's anyway a discrete lattice. Whatever be the distance is not something that's particularly important for us. And in particular, the walker is not allowed to stay on the same node at any time. So you have to keep walking all the time. So the first question is, after walking n steps, what is the probability of locating the walker at some position? So in other words, you're asking probability of let's say you can say x is ml. M is an integer. And so let's now try and get some results for this one. So there are many applications of this. We saw some of those things. So here M, so we need to fix the number of steps, and let's say that I'm going to do a n step walk. Yeah, every time is also discrete. So no, you can't jump. You can't jump over lattices. You can only go to left or right one step away. Yeah, and this is a thing. So when I say that, okay. So when I say that I am taking a n step walk, it means that time is also equal to capital N. Okay. So I have at my disposal that I can do n steps, and some of those steps will be to the left, some of those steps will be to the right, and quite randomly done. Okay. Now I want to get this quantity Pn of m. Probability that probability of finding the particle at x equal to ml in a n step walk. Okay. So now let's fix a few notions. So I'm going to do this in some detail, and then I'll skip over many things first, because this is sort of basics. So I'm going to assume that you will be able to do n1 steps to the right and n2 steps to the left, such that n1 plus n2 is equal to capital N, because we have fixed the total number of steps that can be taken. So now you can write your net displacement, how much you actually moved. Okay. So give it a different this one, that will be simply n1 minus n2. So net displacement could be positive or negative. And you can rewrite it slightly differently. So m is n1 minus n2, and you can use the fact that n1 plus n2 is constrained by capital N, which means that you could write it as n1 minus n minus n1, which is also equal to 2n1 minus capital N. Okay. You will notice that again something, if you think for a second, you will realize that if n is odd, m is also odd, and if n is even, so is m. So one of the important assumptions is that the successive steps of a random walker are statistically uncorrelated. See, for example, a very extreme example of a correlation would be like taking the step only in one direction. So if you're doing an n-step walk, no surprises, you will just be, you will be n lattice sites away from 0 in the same direction. Okay. So that's an extreme example of being correlated. So which means that this also puts in another constraint that if I have to take the next step, I don't need to worry about where I came from. I started from position 0, maybe went left and right and so on, all that is immaterial. I just need to know where I am at this moment and just decide where to go next, that's all. So the past is immaterial. So in that sense, it's a process that is completely uncorrelated from its past. Now, what are the ways in which, so there are, even within the constraint of taking n1 steps to the right and n2 steps to the left, you can do it by making different choices. For instance, you could have you can take n1 steps with probability p and maybe n2 steps with probability q. Okay. And this probability would simply be, since it's uncorrelated, you just need to multiply the probabilities. Okay. So this will be like p to the power n1 and q to the power n2. Now you ask the question, in how many ways can this be done? Because you may not exactly take n1 steps to the right once and all the n2 steps later. Okay, it's going to be all jumbled up, which means that there are very many ways of exactly achieving this. Okay. And the number of ways. So I have written some explanation for this, but I think about it. It's a very simple question. Okay, because n1 steps among themselves are indistinguishable. N2 steps among themselves are indistinguishable. Okay, so it's like you have a pot in which there are red and blue balls, and the red balls among themselves are indistinguishable. Blue ones are also indistinguishable. So you are just asking how many of such types are there. Okay, so this is a number that we need. You can check with simple cases, like if you had n equal to 3, you can work out yourself and see if this formula is there. So now you can write the probability of taking n1 steps to the right. Which I am going to denote by okay. So capital N is the total number of steps, and this and 2, and of course q you can replace by 1 minus p if you want. Okay. And this, you recognize this distribution, it's a binomial distribution. Okay. Now we can write it in terms of m. So I'll just write everything in terms of. So we have two sets of numbers. So we have n1 and n2, number of steps taken to the left and number of steps taken to the right. But you also have the other one, which is n and m. So you can trade in n1 and n2 for capital N and m. You don't lose any information. You're just, it's possible to go from one set of numbers to, it's just a simple change of variables. And in fact, n1 will simply be this, and n2 will be n minus m. So it's okay to use either of these set. So now if I have to express the same probability, so now you can eliminate n1 and n2 from the binomial distribution that we had here, but instead write it in terms of n and m, in which case your result would look like this. And for the special case when P is equal to Q equal to half, this would be the case of an unbiased walk, because the probability of taking a step to the left and a step to the right is equal. So this is a unbiased random walk. In this special case, your Pn of m would simply boil down to and power n. So now what we want to, so what we now have is the distribution. So this is the central result from which you can derive everything, you can answer all the questions that you ask for. The distribution comes about because it's a random process. Okay. There's no one specific answer. So suppose if you want to simulate this, you simulate a random walk on a computer. To simulate this, you need to repeat the random walk process again and again many times. Only then you will get a distribution. Otherwise, if you start from 0 and just get one realization of it, or in other words just do one realization of the random walk, you will actually go to some particular point. You will get one value of m, but you need a distribution. So one of the exercises that I had sent is to actually recreate this distribution from simulations. So you should remember that you need to do a ensemble calculation. Okay. So now let's calculate the mean and variance of this. Let's calculate the mean and variance of this distribution. Just to give you a pictorial idea of what it is, so a binomial distribution is a discrete distribution, so it's going to look something like this. Depends on the parameter, but let's say for some set of parameters, you're going to get something like this. Okay. So you're asking the question, so this is your, so you're asking the question, what is the mean? So in other words, you're looking for maybe the average here, so maybe some point somewhere here. Okay. And when you ask for variance, you're asking for, I got the mean, but how much is it spread out? Okay. So it's like asking something, asking for this, the spread about the mean. Okay. So you understand the physical meaning of mean and the variance, right, from the distribution. Okay. So it's one thing to say, for instance, a cricketer, a new cricketer who has come in maybe in 2 innings has made 2 hundreds. Okay. There was someone who did this recently, right? Forget his name. So you could say, oh, he's better than Tendulkar. His average is only 50, but here is someone who in 2 innings has made 2 hundreds. Average should be 100. Okay. But then the variance is large for such cases where the number of data samples is very less. Okay. So which is why here you need to run your random walk many times to be able to construct a distribution in which you have a reasonable amount of confidence. And then you ask the question about what is the mean and how is the spread about the mean. Okay, so I think if I continue at this speed, I won't be able to cover much. So I will not show you the derivation for how to derive the mean. I will leave it as an exercise for you. Like you start from this distribution, there is a simple trick involved in calculating the mean from this. Mean is 0, yeah, that's true. But how do you actually show that it is 0? But it's 0 only for unbiased random walk. Yeah. Okay, so the mean in general is not 0. So the mean, let me, yeah. Okay, so if we are going back to the other distribution, this one, and you ask for what is the mean of this distribution. In other words, you are asking question about this, and this is simply equal to n times p in general. You can translate it in terms of m as well, and if you do that, I mean, which means that you should use this distribution and compute the mean. I'll just write down the result here. So it is m into p minus q. So when p and q are equal to half for the unbiased random walk, the mean is 0. Otherwise, in general, even from a physical intuition, you can imagine that if you're biased towards one side, the mean is unlikely to be 0. What about the variance? The next question we're asking is, this is actually the standard deviation, but let's say that square of this is variance. We want that quantity, and this sigma m square. So again, I leave it to you as an exercise to derive both these things. So one is this one, and other is this quantity. So you notice that both the mean and this sigma is the variance, they are time dependent. So which means that mean keeps moving as a function of time, and sigma, the variance, also keeps moving as a function of time. So then how does it all be consistent if something like what I have drawn there is the distribution? Is there a chalk here? Okay, so what you have is a distribution in the continuous limit. It would look something like this. Okay, this is 0. Let's say that you're taking p equal to q equal to half, the unbiased random walk. Okay, and this is the measure of your sigma. Okay, and this is your mean. Now, as time progresses, in the unbiased case, what happens is this distribution will become something like this. Okay. So the height will keep decreasing because it's reaching out to larger and larger distances from 0, and the net effect of that is that this variance increases with time. Okay. So now you see that it's more broader. So as you keep simulating it or doing a random walk for longer and longer times, this distribution is going to stretch out. Okay. So net effect is that the variance is going to increase as it stretches. So physically what happens is that for the unbiased random walks, you will keep coming back to 0, which is why the mean stays 0. For the unbiased random walk, but sigma is time dependent, depends on n. Okay, so this is how sigma can increase, but mean does not increase. So in other words, a random walker, an unbiased random walker, will repeatedly visit the 0 site, the starting point again and again. Okay, so this is the central result. You can see that sigma m square, apart from all these factors of 4, p and q, is proportional to n, which means that sigma m is proportional to square root of n. So you could, as I said, think of each time step, each step taken as one unit of time in this model, and hence you can translate this to mean that the distance traveled is proportional to square root of time. So this sigma m proportional to root n, or distance being proportional to square root of time for which the process has been going on, this is a signature of all diffusive processes, or at least standard diffusive processes. So you may or may not be doing a random walk. You could think of the Brownian motion, if you know about it. So a larger molecule which is hit by smaller atoms, and then the larger molecule starts executing a random walk. So there also you do see diffusive process will go as square root of time. Yeah, that's right. This is the mean distance, average distance traveled from position 0.
Yeah, but so here the equation would be then from the previous slide 2 root n root pq.
Yeah, that's right. So if you want the exact distance, so we are only looking at the time dependence.
Right, but in the previous slides, in your slide,
Yeah.
so in your slides there was a
Oh, in the PDF. Just a minute.
yeah, that was
Oh, I see. Mean r square. No, that's okay. Mean r square is basically sigma.
no, but the 2 factor is for
Oh, I see. You mean I missed out a factor of 4 there. Ah, yeah, 2 factor. Okay, that's a missing factor. Yeah. Yeah. Sigma square is proportional to n. Yeah, correct. Maybe there was a mistake in the slide. Let me see. No. So,
r would be that, right?
yeah, sorry. Mean of r square would be more like sigma square. So, I think that should have been n there. Okay, yeah, maybe let me write it out. So, if I use those terms, see this mean r square is like sigma square. This should have been simply something proportional to n. Okay, so the next line shows it correctly. The distance traveled is square root of time. So the mistake there is it should have been n. Yeah. Yeah, it's like it's like total distance traveled. Yeah, not like mean free path. Mean free path is like distance between some collisions of some kind. Yeah. So, for example, if you simulate this again, this is one of the exercises that's given. So, you can plot the distance traveled by a random walker as a function of time. It will go as root t, but when you want to verify this root n law, you take log on both axes. You will get a line like this with the slope half. So which means that if you are going to do a simulation, you have to keep increasing capital N, and for every capital N, you have to do many simulations. Okay, so let me now show you some this one. How does it look in practice? Let's say I'm going to do a 1000-step simulation here. So this is how it will look like. One realization of a random walk. As you can see, the position is on the vertical axis. Okay, so it starts from 0. And subsequent positions are marked as a function of time. I think it comes out better in this. Yeah, now it's better. Yeah. So now each time I press this, you will see that you will get a different realization. See, for example, each time I click on this walk 1D, so you are never ever going to get precisely the same realization of the random walk again, simply because the next step is determined by a toss of a coin. What is? X is time.
And then what is the y-axis?
Y-axis is the position. So you start from 0 position. Yeah, so you fix your time. You say that I'm going to do 1000-step simulation. So this is the full path, for example. So you can see, for example, it started from 0, but twice later it passed through 0 again. So it's going to keep returning to 0 again and again. Let's do a. So you can see that it returns to 0 many more times. But then you can ask, if this is a realization of a random walk, where is that distance going as root n? Okay. How do I sort of infer that from this figure? This is the actual simulation. You can do it on your computer as well. So, so this green line that you see, this is that root n relation. Okay. So again, x-axis is time, y-axis is the position. Your theory says that distance goes as root of time. So that green line is that theoretical envelope. Okay. And what is shown is one realization of the random walk in red color. Okay. Now I can, let me do, yeah, so maybe let me do, yeah. So you can see now here it has done several realizations of the random walk. Okay. So none of that actually passes through that green line, except probably one of them, but that too only partially. Okay. So the key is that these are averaged results. So if you want to realize this, you need to average over many realizations. Only then you will see that, you will realize that root n relation. Okay. So that is the exercise that I have given for you to try it out. Okay. So in a single realization, you cannot expect the analytical result that you get to hold good. So each of this is a random walk path. Each of these colored wiggly lines that you see here. So remember that you had a binomial distribution earlier on. So this is the binomial distribution that we had. In the limit when n becomes very large, this actually tends to a Gaussian distribution like this. Which also means that we can realize that here as well. So I can write two different versions of this distribution. Again, the proof takes several steps of algebra. If I do that, I think next 1 hour will be spent only on that. So I will not do that. Let me just write out the result for you. So you can identify what is sigma here. So this would simply be 2 pi. Or equivalently, you can write it in terms of m, since m is related to continuous values of x like this. In our case, you can do one more translation and write it in terms of x. If you do that, the final distribution will turn out to be something like this. Sigma. So there are two parameters here. One is mu, which is the mean, and other is sigma. Okay. And this mu and sigma, as we argued, this is of course the standard deviation. And this sigma is proportional to root n. So you can see that where the time dependence comes in. It comes from the fact that sigma is root n, and that is sitting in the denominator of the exponent. Okay, so which is why your distribution itself is changing with time. Okay, that's right there in the dependency. Sigma square is NPQ. Yeah.
The 4 was a typo.
Hmm?
It was not 4 NPQ.
Which one?
Earlier you were telling sigma square was 4 NPQ.
No, there is some change of coordinates that has happened here. That is why. So I think you should. This actually goes to the limit where the positions become continuous instead of discrete. Okay. So the fact is now you've got a Gaussian distribution. So this is your standard Gaussian distribution or normal distribution. So your usual normal distribution, you will write it as apart from some constant z power minus something like this. So typically it would look as a function of x. Now we are taught throughout our whatever we had studied that this is something that that shows up in many natural phenomena all over the place. That's why it's called a normal distribution. Okay. And one of the reasons is also this kind of a process where the process itself is subject to random decisions at every time. So this is nicely shown in this. Let me show this video. I don't know if you've heard of this Galton's board. Heard of this? You've seen this? Okay, so it's sort of simulates a random walk in a much simpler way. So what you have is you can drop a marble through a series of these projections that are there, these ones. So the marble actually gets hit randomly by these projections, and our theory says that ultimately the distribution of position should be Gaussian. In fact, that is what you will see here. So the marble starts falling from the top, and this is the Gaussian that you expect, that yellow line. So when the marble falls from the top, it is hit by a large number of those projections. So you can see that it closely approximates a Gaussian. I'll put up this link, or you just type Galton board in YouTube, you will see many simulations of this. So you can see that it rises up and nearly is a nice Gaussian. This is a device, small device you can buy in many markets, though I have not seen it in India.
Some science centers.
Yeah, some science centers and so on, they sell it. Okay. But so here, where is the random walk here? There's no walk at all. But the fact that at every point as it falls through that series of nails or whatever, it randomly decides between going this way and this way in some sense. Okay. So that's like a random walk. So you can see that random walk is a simple process, a random process on a line, but finally kind of models any other process where you have to make a series of random decisions. So that is where the power of that model comes from. You might be randomly deciding on many choices, including going for a movie versus attending a class like this and so on. But all of that, at the core of all of that is the idea that you will have to take a random decision, and a series of random decisions like that, the limit when the numbers are large, would finally lead to some relevant distribution becoming a Gaussian. So there is a more general version of this random walk problem which is often used. So this is one specific version. In fact, this is not the only version of the random walk problem. A more useful version in many contexts is goes something like this. So here, so you start with, as usual, you can set your initial condition that x0 is equal to 0. That's equivalent to saying that the random walker would start from position 0. And this is your dynamical equation. So it's a difference equation. And this Sn that you have here, it's a random number. So typically it's a random number from a Gaussian distribution. You can try other distributions as well, but this is one usual choice that is made. But the important point is that this Sn should be a random number that is uncorrelated. Okay, it should be maybe a Gaussian distribution or some other distribution, but it should be uncorrelated. Yeah, what's your? No. So Sn is plus or minus 1 is exactly the random walk that we saw. So here it need not be exactly plus or minus 1, it could be any real number. Yeah. So it's no more identical to the previous version of the random walk that we saw. So here the thing is that Sn could be a randomly chosen number, that's all. That is where the randomness comes from. Yeah. So once again you can do the math. Here also you can calculate the mean. For example, you can ask what is the mean position as n tends to infinity. You can ask the same question of what is mean of x square as n tends to infinity. You will get pretty much the same qualitative results. So here also the mean of x square, that is sigma, goes as square root of time and so on. Yeah, for example, if I have to write an expression for the position, it will simply be, given that I have chosen x0 to be 0, it will simply be s0 plus s1 plus sn. Okay, that's the position. In other words, it's simply this summation. So the important assumption is that each of these steps that you take, the numbers that you draw from the distribution, they are uncorrelated series of random numbers. Yeah. So uncorrelated would mean that if you calculate the correlation, autocorrelation, it should decay instantly. So for example, you calculate the autocorrelation, which would be something like this. So if I try to plot it, It will start from 1 by construction, but then it will decay to 0 and stay there. It will look something like this. So autocorrelation is essentially you're comparing. Okay, so let's say that I have some sample series like this. Okay, xt as a function of time. Okay, so you are asking the question: if I move it, let's say one step ahead, is it still correlated? Yeah, in time. So you take another copy of this and just shift it one step, two step, three steps, and so on. Does it correlate with the rest of the time series? Okay. So if it correlates, typically it means that you have some memory in the system. So in this particular case where you claim that it's uncorrelated, the autocorrelation function would drop down and would stay at 0. So this means that it is uncorrelated, which means that it has no memory of its past. Compared to autocorrelation, which might drop like this has some finite memory. Probably it's going towards 0, but at least over some time it has some memory. Okay. So there are many natural processes are of this type. They do have some memory in the system. So in fact, you see, for example, repetitions of day, night, seasons, and whatever, pretty much any natural process you take, it keeps the memory. If it were random, you can't expect a winter to precisely come back a year later, and so on. But for this purpose, of course, we are simulating something very special where we want randomness as the core property. So you need to take numbers from a certain distribution, but that doesn't remember the past. You can construct such series of numbers. So if you if you go to your computer and use one of these RAND functions or RAND function, it precisely gives you an uncorrelated random number, typically from a uniform distribution. Tau is the shift. So I can actually write for you the actual. Let's say that x of t is my basic series. Okay. So this c of tau will be x of t minus. Let's say for simplicity, I'll assume that mean is 0. So it oscillates about this, so that I don't have to subtract this. So this is your autocorrelation function. So you have your original time series and you have a shifted series. Okay. So you're asking the question, how similar are they? So suppose, let's say you have a periodic function like a sine function. So if you shift the sine function against one, after a period of 2 pi, it will exactly coincide once again. So it comes back to itself again. Okay. So there it never forgets where it came from in some sense. So it will repeatedly be after 2 pi, 4 pi, it will precisely coincide. Whereas a random uncorrelated function like this will never do that. Yeah, by construction, this correlation function will always lie between 0 and 1 or minus 1 to 1. So 1 would mean that it is strongly correlated if it is always 1 as a function of tau. And 0 is uncorrelated, minus 1 is anti-correlated. So if you take two processes where one is, let's say, increasing and other one is decreasing when one increases, if you compare two of them, but typically for these kind of cases, 0 to 1 is sufficient. So it's either uncorrelated, this is the correlated limit. Anywhere in between, essentially it means that it has some amount of correlation. See, ideally you should take, typically you won't be able to do this summation to infinity. So, you can only get a sample of your correlation because obviously you have finite data. Yeah. Ideally, autocorrelation converges only in that limit where you have infinite sample. Just to recollect what we have done, so we took the simplest possible model of a random walk on a line and basically showed that the distribution over positions would be a Gaussian whose variance is time dependent. And this kind of relation, distance going as square root of time, is characteristic of all diffusive processes. Diffusive processes would mean that a process where the process happens through a sequence of random decisions or random events. Okay, so I think I'll skip a lot of this. I was going to prove that the unbiased random walk is recurrent. So, I'll just tell you what this means. Recurrent would mean that, let's say you're starting from 0, what is the probability that it comes back to 0? Okay. So, the result is that for one dimensional random walk that's unbiased, that probability is 0, probability of recurrence, or it's just called recurrence. In fact, recurrence is 1, not 0. So, it is guaranteed to return to its starting point. Given enough time, because there's another quantity called the first passage time. So, let's say you start from position 0, how long after are you coming back to that? Actually, that diverges to infinity in the one dimensional case. So, which means that if you have the patience to wait for infinite time, ultimately you will see that it will come back. It's guaranteed to come back, but not in any short time that you want it to do. So, that's again a very characteristic of one dimensional unbiased walk. Okay, now I think I'll maybe just stop this lecture with this connection with the diffusion equation, and after that we'll actually go ahead with looking at the same process in terms of Markov chain. So, then we will connect it up with all these PageRank algorithms and other things. So, that is for the next lecture in the afternoon. So, this looks like a very, the random walk problem that we did might look like a very cooked up problem, because whoever does that, you might ask. Why would anyone do a random walk of that type, that too on a integer lattice? There is nothing like an integer lattice in real life. So, you can get better by actually going to a more continuous lattice. You could say, for example, that I will still consider a random walk on one dimension, but instead I would say that maybe with probability p, I will make a jump with delta x. And with probability q, I will make a jump uh, one minus p, which is equal to q. I will take a jump of magnitude minus delta x. Okay. Then you could ask your question, what is the probability that the walker is at position x at time t, given that the walker started at position x0 at time t0. So, the question is, what is this? Similar to the question that we asked there, is just that now the the setting of the problem has changed slightly. So to answer this question, this is what we want to do. Again, the answer is not at all surprising because we already know the distribution and everything. Nothing of that changes qualitatively. But now you can actually write a differential equation for the process, okay, if you follow this, this route. So P of x comma t starting from x0 t0 will be some small p, that is this one, plus q into capital P of okay, this is a very straightforward equation. So now you can write it in terms of PDF by saying that this probability is simply equal to f of x comma t x0 t0 into delta x. So you can do all that, and finally what you would do is that you will expand, like you have this term for example here. So this will be something like x minus delta x comma t minus delta t. So you can expand this as a Taylor series about x and t. Okay. And similarly you can do this here as well. Do a Taylor expansion. You are aware of Taylor expansion, right? Okay. So you can do a Taylor expansion about x and t, and again I think I'll so if you do the Taylor expansion, cancel off many terms, finally you will get to this equation. So now you are on a sort of familiar territory in the sense that typically one learns to solve differential equations given initial conditions. Now you don't need to worry about lattice points and all these combinatorial kind of calculations that we did. All that is unnecessary. You have a nice differential equation, a partial differential equation. Just specify the initial condition or the boundary condition and then solve this. And the standard diffusion scenario comes when your mu is equal to 0. This is often called the drift term. And this is of course the one which is responsible for diffusion. To understand physically what it would mean, suppose let's say that I have this closed room and I keep maybe a scent bottle at one corner, okay, and you would physically expect that after some amount of time, if I'm going to stand in this corner, that smell will finally come and hit me after some time, okay. So that is a diffusive process because the molecules of that scent are being hit by the gas molecules, and that is exactly like a random walk. And finally it spreads in all the directions, and you will of course finally get it. The drift comes when, suppose let's say there is a draft of breeze coming in particular direction, that actually lends a drift to it, apart from the random motion that it is doing and is also moving ahead. But the drift will actually give it a push and makes it happen faster. So you can, in the standard diffusion case, you assume that there is no such drift. It's equivalent to saying that there is maybe no special wind or anything like that which is making it move in one particular direction. So, in the absence of that, the only process that happens is the diffusive process, the randomness. So, in fact, this term is called the drift term or a convection term, and the second term is called the diffusion term. So, again, I am not going to solve this, but yeah. What is D naught is the diffusion coefficient. Okay, I see. I can write it in terms of D naught, for example. Again, since I didn't go through the whole derivation, I am not. So it's the limit of this delta x and delta t tending to 0 of 2 delta t. So this is D naught. So, to summarize everything that we have said, so there is a discrete problem of random motion on a lattice, but you can also treat it as a continuous problem, but the core ideas remain the same. That if your process is going to be affected by a series of randomness, sigma will go as square root of t, square root of time. Whether you see it in a continuous process using a diffusion equation or see it in the standard random walk process, whatever, that result is the same. Or in fact, in any unknown process, if you look, if you see that no distance goes as square root of time, you can more or less claim that it is a diffusive process. Because in the other thing which you must have learnt, which would be a ballistic motion, you have the standard formula that S is equal to ut plus half t square, right? So if you have written these entrance exams for whatever it is worth, you would have kind of had this formula by heart. So here distance goes as t square for large times. Okay, so that would be a ballistic motion. Whereas in a diffusive process, the same distance goes as square root of t. So its diffusive process is slow. Ballistic would simply mean that I am straight away going. I need to know I know where I am going. I just go there. I don't do this left and right decisions and so on. So that's the difference. So in the next lecture later in the afternoon, I guess, we'll now we'll now actually use a very different way of looking at diffusive processes. Okay. Randomness will still be there, but use a different machinery called these Markov chains. That actually connects it up with things probably you must have studied in computer science. Okay. So that is where we are headed, and that's what we are headed in the next class.